In the furthest reaches of our solar system, there exists a boundary so profound, so absolute, that it might as well be the edge of reality itself. We like to think we know our cosmic neighborhood. We've mapped the planets, tracked asteroids, and sent our robots to dance with distant worlds. But what if I told you that 99.9% of our solar system remains completely invisible to us? What if the very edge of our cosmic home is shrouded in such impenetrable darkness that we can't even prove it exists? This is the mystery of the Oort Cloud, a ghostly shell of ice and rock that may surround us at distances so vast, so incomprehensibly remote, that they challenge the very notion of what we can call real. Join me as we venture into the cosmic void, where the laws of physics conspire to blind us, where our most powerful telescopes fail, and where the question becomes not just what lies beyond our sight, but whether the boundary of observation is the boundary of existence itself. Before we dive into this cosmic mystery, let me know where in the world you're watching from and what time of day it is for you right now. I'm curious to know how far this journey will take us across our own planet. Drop your location and time in the comments below. Picture standing on the observation deck of the world's most powerful telescope, gazing out into the cosmos with instruments that can spot galaxies billions of light years away. You can see the birth of stars in distant nebulae, witness black holes devouring matter at the far reaches of the universe, and detect planets orbiting alien suns thousands of light years from Earth. Yet there's something you cannot see, something hiding in plain sight, right here in our own solar system. Less than 2 light years from where you sit, there exists a boundary so elusive that it might as well be made of shadows. This is our solar system's true edge, a realm that exists in a darkness so profound that it renders our most advanced technology helpless. We call it the Oort Cloud, named after the Dutch astronomer Jan Oort, who first theorized its existence in 1950. But here's the unsettling truth. We have never actually seen it. Think about that for a moment. We can photograph the surface of Pluto in stunning detail. We can track asteroids the size of school buses, millions of miles away. We can detect the atmospheric composition of planets in other star systems. But we cannot see the very boundary of our own cosmic home. The Oort Cloud represents more than just an observational challenge. It represents a fundamental limit to human perception. Imagine living your entire life in a house, knowing every room, every corner, every detail of your dwelling, only to discover that there are walls you cannot see, boundaries you cannot detect, and rooms that may or may not exist. This is humanity's relationship with the Oort Cloud. What makes this invisible boundary even more mysterious is its sheer scale. If our solar system were the size of a coin, the Oort Cloud would extend outward like an invisible sphere, the size of a football field. Within this vast dark realm, trillions of icy objects drift in eternal night, so far from our sun that they receive less light than a candle flame provides from a mile away. The implications are staggering. We navigate through space, plan missions to distant worlds, and calculate the gravitational influences on our planets, all while remaining fundamentally blind to the very structure that defines our solar system's outer limits. It's like trying to understand the architecture of a building while being unable to see its walls. This isn't simply a matter of building bigger telescopes or waiting for better technology. The Oort Cloud's invisibility is written into the fundamental laws of physics themselves. The mathematical relationship between distance and brightness ensures that these distant objects exist in a realm beyond human perception, trapped in a darkness so complete that they become effectively non-existent to our instruments. Yet they are there. We know this not through direct observation, but through the ghostly visitors they occasionally send our way, comets that plunge toward the sun, carrying tales of the frozen wastes beyond. These cosmic messengers are our only proof that the invisible boundary exists, like letters thrown over a wall from a country we cannot see. As we embark on this journey to understand why we cannot see past the Oort Cloud, we're not just exploring the limits of technology or the challenges of astronomy. We're confronting a fundamental question about the nature of reality itself. If something exists but cannot be observed, does it truly exist? And if the boundary of our observation becomes the boundary of our known universe, What does that mean for our understanding of what is real? The Oort Cloud is astronomy's greatest paradox, a structure so massive it dwarfs everything else in our solar system, yet so ethereal it might as well be made of whispers and shadows. Imagine a spherical shell of ice and rock, stretching from roughly 2,000 times the distance from Earth to the Sun, all the way out to halfway to the nearest star. This isn't just big, this is incomprehensibly vast. If you could somehow travel at the speed of light, it would take you nearly 2 years to cross from the inner edge of the Oort Cloud to its outer boundary. Yet, despite containing an estimated 1 trillion objects, some as large as mountains, we cannot see a single one of them directly. The Oort Cloud exists in a state of perpetual twilight, but makes the deepest ocean trenches seem bright by comparison. These objects orbit our sun so slowly that a single trip around takes millions of years. They are the solar system's most ancient residents, frozen in time since the very birth of our cosmic neighborhood 4.6 billion years ago. They are repositories of pristine material from the early solar system, cosmic time capsules that have remained virtually unchanged since the planets were forming. But here's where the ghost story truly begins. The Oort Cloud was never discovered. It was deduced. Jan Oort didn't peer through a telescope one night and spot this distant realm. Instead, he looked at the behavior of long-period comets, those spectacular visitors that appear in our skies once every few centuries or millennia, and worked backward like a cosmic detective. These comets arrive from every direction in space, not just from the flat disk where the planets orbit. They come from above, below, and from all sides, as if our solar system were surrounded by a spherical shell of icy objects. When Oort calculated where these comets must originate, he found they came from distances so vast that the sun would appear as nothing more than a bright star in their sky. The mathematics were elegant and undeniable. The observations fit the theory perfectly. There had to be a vast reservoir of cometary material surrounding our solar system, like an enormous invisible bubble. The Oort Cloud wasn't just a hypothesis, it was a logical necessity, yet it remained as intangible as a mathematical equation, as real as gravity, but as invisible as time itself. This creates a peculiar situation in astronomy. We base our understanding of the solar system's architecture on a structure we cannot see, cannot photograph, and cannot directly study. We know it exists because the alternative, that long-period comets somehow materialize from nothing, violates everything we understand about physics and orbital mechanics. The Oort Cloud challenges our very definition of existence. It forces us to accept that reality extends far beyond the boundaries of human perception. In a universe where seeing is believing, the Oort Cloud teaches us that some of the most fundamental structures in our cosmic neighborhood exist in a realm beyond sight, beyond direct detection, and almost beyond imagination. As we prepare to explore why this ghostly presence remains invisible to us, we're embarking on more than just a scientific investigation. We're examining the very limits of human knowledge, on the boundaries between the known and the unknowable. There's a cruel mathematical law that governs our universe, one that ensures the farther we look into space, the more reality fades into darkness. It's called the inverse square law, and it's the reason why the edge of our solar system might as well exist in another dimension. Let me paint you a picture that will change how you think about cosmic distances forever. Imagine standing in a field at night, holding a flashlight. At 10 feet away, your beam illuminates objects clearly. At 20 feet, they're dimmer, not just a little dimmer, but 4 times dimmer. At 40 feet, they're 16 times dimmer. This isn't just inconvenient. It's a fundamental law of physics that makes distant objects disappear into mathematical oblivion. The inverse square law states that the intensity of light decreases with the square of the distance. Double the distance, and you get 1/4 the light. Triple it, and you get 1/9. This might seem like a gentle fade, but when you're dealing with astronomical distances, this law becomes a cosmic executioner, systematically erasing objects from our view. Now, let's apply this to the Oort Cloud. Objects in the inner Oort cloud orbit at distances roughly 2,000 times farther from the Sun than Earth does. That means they receive 1/2000 times as much sunlight as we do. That's 1/4 millionth the amount of light. To put this in perspective, if Earth receives enough sunlight to power a 100-watt light bulb, an object in the inner Oort cloud receives enough to barely power a grain of rice-sized LED. But we're not done with our mathematical journey into darkness. Objects in the outer Oort cloud sit at distances 100,000 times farther from the Sun than Earth. The amount of sunlight they receive, 1/10 billionth of what we get. That's not dim, that's virtually non-existent. But we're not dim, that's virtually non-existent. The Sun, from that distance, provides less illumination than a birthday candle held 3 miles away. Here's where the physics becomes truly unforgiving. For us to see these objects, they need to not only receive sunlight, but also reflect it back to us. This creates a double penalty from the inverse square law. The light has to travel from the Sun to the object, weakening by the square of the distance, bounce off the object, and then travel back to us, weakening by the square of the distance again. The result, objects in the Oort cloud reflect approximately 1/4,000,000th. That's 1 followed by 15 zeros, the amount of light that Moon reflects. To understand just how faint this makes Oort cloud objects, consider this comparison. If the Moon were moved to the distance of the inner Oort cloud, it would become 16 trillion times dimmer than it appears now. Our most sensitive telescopes, the ones that can detect galaxies at the edge of the observable universe, would struggle to spot something as large and reflective as our Moon at Oort cloud distances. But the inverse square law is just the beginning of our visibility problems. These objects aren't conveniently bright and reflective like the Moon. They're typically dark, made of rock and ice, that reflects only a small fraction of the already negligible light that reaches them. Many have surfaces as black as charcoal, absorbing rather than reflecting what little light they receive. The temperature at Oort cloud distances hovers just above absolute zero, around -440 degrees Fahrenheit. At these temperatures, these objects emit almost no heat that we could detect with infrared telescopes. They exist in a thermal wasteland, too cold to glow with their own heat, too distant to shine with reflected light. This creates what astronomers call the visibility horizon, a distance beyond which objects of a given size simply disappear from our ability to detect them, no matter how perfect our instruments become. It's not a technological limitation, it's a fundamental boundary imposed by the laws of physics themselves. The cruel irony is that while we can detect massive black holes billions of light years away, because they're actively consuming matter and glowing brightly, we cannot see mountain-sized objects in our own solar system. Distance, combined with the inverse square law, has created an impenetrable veil around our cosmic neighborhood. Consider the largest telescopes ever planned. Even if we built a telescope the size of a football stadium, filled it with perfect detectors, positioned it in the ideal location in space, the inverse square law would still render Oort cloud objects effectively invisible. The mathematics are unrelenting and unforgiving. This isn't just an academic exercise in physics. It represents a fundamental limit to human knowledge. Or there are regions of our own solar system that exist beyond the boundary of possible observation, whole, trapped in a darkness so profound that they might as well be in another universe. The inverse square law has created a cosmic censorship, hiding the very architecture of our solar system behind an impenetrable mathematical veil. What's perhaps most unsettling is that this same law applies everywhere in the universe. Every star system, every galaxy, every cosmic structure is surrounded by invisible boundaries, where reality fades into mathematical darkness. We live in a universe where the majority of what exists remains forever hidden from our view, not because of technological limitations, but because of the fundamental nature of light itself. As we continue our journey into cosmic invisibility, remember that we're not just exploring the limits of astronomy, we're confronting the boundaries of what can ever be known about our own cosmic home. Between our sun and the nearest star lies an abyss so vast and empty that it defies human comprehension. a void where darkness reigns supreme, and where the very concept of illumination becomes meaningless. This interstellar wasteland is where the Oort Cloud makes its home, suspended in a darkness so complete that it makes the deepest ocean trench seem like a brightly lit room. Or to understand why we cannot see past this boundary, we must first grasp the profound nature of this cosmic darkness. Imagine if you could somehow turn off every light source in the universe except for our sun. Now, travel outward to the Oort Cloud and look around. The sun, which fills our sky with brilliant light and warmth, has become nothing more than a bright star, brighter than any other star in the sky. Yes, but still just a point of light incapable of illuminating the vast darkness around you. The nearest star to our solar system, Proxima Centauri, lies 4.24 light-years away, or that's roughly 25 trillion miles, or about 6,000 times farther than the outer edge of the Oort Cloud. The light from Proxima Centauri, already feeble when it reaches Earth, becomes essentially non-existent by the time it reaches the outer solar system. Any objects in the Oort Cloud are suspended in a cosmic no-man's land, too far from our sun to be illuminated by it, and far too distant from other stars to receive any meaningful light from them. This creates what astronomers call the cosmic dark zone, a region where objects exist in a state of illumination so minimal that they become ghosts in the cosmic machinery. Unlike planets closer to the sun, which bask in enough solar radiation to be clearly visible, Oort Cloud objects exist in a twilight realm where the very concept of brightness becomes academic. The mathematics of this darkness are staggering. The combined light from all the stars in our galaxy, when it reaches the Oort Cloud, provides less illumination than a full moon provides to Earth. Imagine trying to photograph a charcoal briquette on a moonless night while wearing sunglasses. This gives you some sense of the observational challenge we face. But the darkness problem goes deeper than simple lack of illumination. The interstellar medium itself, the thin soup of gas and dust that fills the space between stars, acts like a cosmic fog, absorbing and scattering what little light exists. Over the vast distances involved, even the negligible starlight that might reach the Oort Cloud gets absorbed and redirected, further dimming these already invisible objects. This interstellar absorption creates a feedback loop of darkness. The farther out we look, the more interstellar material lies between us and our target. This material doesn't just block light, it preferentially absorbs shorter wavelengths, causing distant objects to appear not just dimmer, but redder and more distorted. It's as if the universe itself conspires to hide its most distant secrets behind layers of cosmic camouflage. The situation becomes even more challenging when we consider that the Oort Cloud objects are not uniformly distributed. They exist as a sparse population, scattered across an enormous volume of space. The density is so low that if you could somehow stand on one Oort Cloud object, the nearest neighbor might be millions of miles away, invisible even if it were as bright as a lighthouse. This sparsity means that even if we could somehow illuminate the entire Oort Cloud region with artificial light, we would be looking for needles in a haystack the size of a small star system. The signal-to-noise ratio, the contrast between what we're looking for and the background darkness, approaches zero. The darkness between stars also means that Oort Cloud objects have no external reference points. Unlike asteroids in the inner solar system, which can be tracked against the backdrop of distant stars, objects in the Oort Cloud move against a background of such profound darkness that detecting their motion becomes nearly impossible. They are invisible objects moving through invisible space. Perhaps most unsettling is the realization that this darkness is not temporary or technological, it's permanent and fundamental. No amount of scientific advancement can illuminate the space between stars. No future telescope can banish the cosmic darkness that shrouds the outer solar system. The void between stellar systems represents an absolute boundary to direct optical observation. This cosmic darkness forces us to confront an uncomfortable truth. The majority of our solar system exists in a realm beyond human sight, not because we lack the technology to see it, but because darkness itself has claimed these regions as its domain. The Oort Cloud dwells in a shadow so profound that it challenges our very definition of existence within our cosmic neighborhood. When direct observation fails, astronomers become cosmic detectives, using mathematics as their magnifying glass and physics as their fingerprint powder. The story of the Oort Cloud is ultimately a story of brilliant minds piecing together evidence of something that refuses to show itself. The detective work began in the 1950s, when Jan Oort noticed something peculiar about comets. These spectacular visitors to our inner solar system didn't just appear randomly, they followed patterns, mathematical signatures that pointed to a hidden source. Like a detective studying crime scenes, Oort examined the orbits of long-period comets and found clues that would revolutionize our understanding of the solar system's architecture. The first clue was in the numbers themselves. Long-period comets, those that take hundreds or thousands of years to complete their orbits, arrive at the inner solar system with orbital periods that cluster around specific values. This wasn't random. It was mathematical evidence of a source region at specific distances from the Sun. By working backward from the comet's orbital mechanics, Orbital calculated that they must originate from a spherical shell of objects located between 2,000 and 200,000 times the Earth-Sun distance. So, what wasn't random. It was mathematical evidence of a source region at specific distances from the Sun. But the mathematics revealed something even more intriguing. These comets didn't just come from any random direction. They arrived from all angles in space, suggesting their source region was spherical rather than flat, like the disk of planets. This was the smoking gun that pointed to a vast, three-dimensional shell of objects surrounding our solar system, like an enormous invisible bubble. The mathematical detective work didn't stop there. By analyzing the orbits of hundreds of long-period comets, astronomers could estimate not just where the Oort Cloud exists, but how many objects it contains. The numbers are staggering, somewhere between 1 trillion and 100 trillion icy objects, ranging from mountain-sized chunks to bodies larger than asteroids, all orbiting our Sun in the cosmic darkness beyond. These mathematical models also reveal the Oort Cloud's internal structure. The orbital mechanics suggest it's not uniform. There's an inner spherical cloud and an outer shell, each with different densities and compositions. The mathematics paint a picture of cosmic architecture we could never see directly. Modern astronomers have refined these mathematical techniques into an art form. They use statistical analysis to study the orbital characteristics of thousands of comets, looking for subtle patterns that reveal the hidden structure of the Oort Cloud. Computer simulations model gravitational interactions over millions of years, tracing how objects might move through this invisible realm. The mathematics also reveal the Oort Cloud's violent history. By analyzing the orbital inclinations and eccentricities of comets, astronomers can deduce that the Oort Cloud has been stirred and sculpted by gravitational encounters with passing stars. The mathematical signatures in comet orbits tell stories of ancient stellar close encounters that occurred millions of years ago, leaving permanent mathematical scars in the architecture of our solar system's outer boundary. Perhaps most remarkably, these mathematical techniques allow us to predict where individual Oort Cloud objects might be located and how they might behave, even though we cannot see them. It's like predicting the location of invisible planets, based solely on the mathematical shadows they cast on visible objects. The mathematics of detection represent one of astronomy's greatest triumphs, using pure reasoning and numerical analysis to map invisible realms. Through equations and statistics, we've constructed a detailed picture of a region that exists beyond the reach of our senses, proving that sometimes the most profound discoveries come not from what we can see, but from what we can calculate. This mathematical approach to invisible astronomy represents a fundamental shift in how we explore the cosmos, transforming astronomy from a purely observational science into a mathematical detective story, where numbers reveal truths that light cannot illuminate. Every few years, sometimes every few centuries, a ghostly messenger arrives from the darkness beyond, carrying with it the secrets of realms we cannot see. These are the long-period comets, cosmic time capsules that serve as our only direct evidence that the invisible Oort Cloud truly exists. Picture Comet Hale-Bopp, that spectacular visitor of 1997 that graced our skies with its brilliant tail and coma. For months, millions of people gazed up at this celestial wanderer, marveling at its beauty. But few realized they were looking at a cosmic archaeologist, a fragment of the outer solar system that had journeyed for thousands of years to bring us news from the frontier of darkness. Hale-Bopp's last visit to the inner solar system occurred roughly 4,200 years ago, around the time the pyramids of Giza were being constructed. Its orbit carries it out to approximately 370 times the distance from Earth to the Sun, well into the theoretical Oort Cloud region. When it returns in another 2,500 years or so, our descendants will witness the same messenger returning from its pilgrimage to the invisible boundary of our solar system. These comets are more than just spectacular sky shows. They're cosmic messengers carrying physical evidence of conditions in the Oort Cloud. When astronomers analyze the composition of comet nuclei, they're essentially performing forensic analysis on samples from the outer solar system. The water ice, frozen carbon dioxide, and organic compounds found in comets tell us about the chemical composition of the Oort Cloud itself. The story gets even more fascinating when we consider the mechanics of how these messengers are dispatched to us. So, cloud objects normally orbit in the frigid darkness, taking millions of years to complete a single trip around the Sun. They would remain there forever, invisible and inactive, if not for occasional gravitational disturbances that nudge them from their distant orbits. Sometimes a passing star ventures close enough to our solar system to gravitationally stir the Oort Cloud, like stirring a pot of cosmic soup. Other times, the gravitational influence of the Milky Way itself, what astronomers call the galactic tide, provides the push needed to send objects tumbling inward. These gravitational kicks alter the orbits of Oort Cloud objects, sending them on million-year journeys toward the inner solar system. As these objects fall inward, something magical happens. The increasing warmth of the Sun begins to vaporize their icy surfaces, creating the spectacular tails and glowing comas that make comets visible to us. It's a cosmic irony. These messengers from the realm of darkness only become visible by literally evaporating in the light of our Sun. The orbital characteristics of these cosmic messengers provide crucial information about their origin. Long-period comets arrive from every direction in space, above, below, and from all sides of the solar system's plane. This omnidirectional arrival pattern is the strongest evidence we have that the Oort Cloud is spherical rather than disc-shaped, like the region where planets orbit. Some of the most famous comets in history are messengers from the Oort Cloud. Comet West, which dazzled observers in 1976, originated from distances of roughly 70,000 times the Earth-Sun distance. The Great Comet of 1811, visible to the naked eye for 260 days, came from even farther out. These spectacular visitors represent just the tiniest fraction of objects in the Oort Cloud, the few that happen to get nudged onto Earth-crossing orbits where they become visible to us. But here's what's truly remarkable about these cosmic messengers. They're self-destructing. Each time a long-period comet approaches the Sun, it loses some of its material to space. The beautiful tail that makes comets so spectacular is literally the comet dying, shedding parts of itself into the solar wind. Most long-period comets can only make a few dozen passes through the inner solar system before they're completely worn away. This means that the comets we see today are fresh arrivals from the Oort Cloud, recently disturbed from their ancient orbits. The spectacular comet displays we witness are cosmic birth announcements, marking the moment when invisible objects from the outer darkness transform into temporary visitors to our illuminated realm. The timing of these arrivals also tells us about the structure and dynamics of the Oort Cloud. By studying when and how often long-period comets appear, astronomers can estimate the population density of different regions within this invisible shell. It's like studying the population of an invisible city by counting how many people occasionally venture into the visible downtown area. These cosmic messengers provide our only tangible connection to the invisible boundary of our solar system. Every long-period comet is a physical sample from the Oort Cloud. a piece of evidence that something vast and invisible surrounds us in the cosmic darkness. Without these occasional visitors, the Oort cloud would remain purely theoretical, a mathematical necessity with no physical proof of its existence. We live in an age of unprecedented astronomical capability. Our telescopes can photograph galaxies at the edge of the observable universe, detect planets orbiting distant stars, and measure the chemical composition of stellar atmospheres thousands of light-years away. You live in an age of umprari, sinia mangay. Yet when we turn these same instruments toward the outer reaches of our own solar system, they become as helpless as a person trying to read a book in absolute darkness. The Hubble Space Telescope, humanity's most famous eye on the cosmos, can discern details on galaxies billions of light-years away that are smaller than a human fingernail would appear from the distance of the moon. Its resolution and sensitivity have revolutionized our understanding of the universe. But place an object the size of a city in the Oort cloud, and Hubble would be utterly blind to its existence. To understand why our best technology fails so completely, let's examine what it would take to actually detect an Oort cloud object. Consider a hypothetical object, 100 kilometers across, roughly the size of a large asteroid, located in the inner Oort cloud at about 10,000 times the Earth-Sun distance. This object would reflect approximately 1/10 trillionth the amount of sunlight that hits Earth. To put this in perspective, you would need to collect light for roughly 10,000 years with the Hubble Space Telescope to gather enough photons to create even a single pixel image of this object. The James Webb Space Telescope, our newest and most powerful space observatory, represents the cutting edge of astronomical technology. With its massive 6.5-meter mirror and unprecedented infrared sensitivity, it can detect the heat signatures of objects that emit virtually no visible light. Surely this technological marvel could spot objects in the Oort cloud. Unfortunately, the answer is still no. Objects in the Oort cloud exist at temperatures just above absolute zero, around 5-20 Kelvin, or roughly -450 degrees Fahrenheit. At these temperatures, they emit infrared radiation so feeble that even Webb's extraordinary sensitivity cannot detect them. The telescope would need to stare at a single point in space for centuries to collect enough infrared photons to confirm the presence of even a large Oort cloud object. But the challenges go beyond simple detection. Even if we could somehow spot an Oort cloud object, confirming that it actually belongs to the Oort cloud would require measuring its orbital motion. Objects in the Oort cloud move so slowly relative to our position that their motion would be imperceptible over human timescales. An object in the outer Oort cloud might take a century to move through an angle equivalent to the width of a human hair held at arm's length. The problem becomes even more complex when we consider the search strategy. The Oort cloud encompasses a volume of space roughly 125 trillion times larger than the volume enclosed by Earth's orbit. Searching this entire region with our current telescopes would be like trying to find specific grains of sand scattered across an area the size of Asia while blindfolded, and only allowed to examine 1 square inch at a time. Even if we imagine future technological advances, the fundamental physics of detection impose absolute limits. Consider a hypothetical space telescope with a mirror the size of a football field, far larger than any currently conceivable. Even this enormous instrument, equipped with perfect detectors and positioned optimally in space, would struggle to detect Oort cloud objects due to the inverse square law's unrelenting mathematics. The situation becomes more frustrating when we realize that our telescopes can easily detect much more distant objects, but only if those objects are actively generating their own light. A supernova explosion in a galaxy billions of light-years away shines brightly enough to be seen with modest telescopes, while a mountain-sized object in our own solar system remains completely invisible because it only reflects the dim light it receives from our distant sun. Radio telescopes, which have revolutionized our understanding of the cosmos by detecting radio waves from distant galaxies and pulsars, offer no help with the Oort cloud. The objects there are too cold and inactive to emit detectable radio signals. They exist in a state of electromagnetic silence, producing no signals that our radio dishes can intercept. Some astronomers have proposed indirect detection methods, looking for the gravitational effects of Oort Cloud objects on the orbits of long-period comets, or searching for the subtle dimming of background stars Oort Cloud objects pass in front of them. These techniques, called gravitational microlensing and occultation studies, represent ingenious attempts to detect invisible objects by their shadows and gravitational fingerprints. However, these indirect methods face their own overwhelming challenges. The gravitational effects of individual Oort Cloud objects are so minute that they would be swamped by the gravitational influences of planets, asteroids, and nearby stars. Occultation events, when an Oort Cloud object passes between us and a background star, would be so rare and brief that we might observe for centuries without witnessing a single event. Even proposed future technologies struggle with the Oort Cloud challenge. Concepts for space-based interferometers, networks of telescopes working together to achieve unprecedented resolution, could theoretically detect much smaller and dimmer objects than current instruments. But even these futuristic observatories would need to overcome the fundamental limitation imposed by the inverse square law and the minimal amount of light available at Oort Cloud distances. Perhaps most sobering is the realization that this technological limitation isn't temporary. Unlike many frontiers in astronomy, where advancing technology gradually pushes back the boundaries of the observable universe, the Oort Cloud represents a permanent observational horizon. The mathematics of light and distance ensure that these objects will remain invisible regardless of future technological advances. This represents a profound moment in human scientific achievement. We have reached a boundary not of technology, but of physics itself. We have encountered a region of our own cosmic neighborhood that exists beyond the reach of electromagnetic observation, hidden not by engineering limitations, but by the fundamental laws that govern how light behaves in our universe. The Oort Cloud stands as a humbling reminder that even in our own solar system, there are realms that will forever remain beyond direct observation, accessible only through mathematical deduction and the occasional cosmic messenger that ventures into our illuminated realm. To truly understand why we cannot see past the Oort Cloud, we must first grasp distances so vast that they break our ability to comprehend them. We're about to embark on a journey through scales of emptiness that challenge the very limits of human imagination. Let's start with something familiar and work our way outward into the cosmic void. The distance from Earth to the Moon is about 240,000 miles, a distance that seems vast until you realize that light covers this gap in just over 1 second. The distance from Earth to the Sun, about 93 million miles, takes light roughly 8 minutes to traverse. We call this distance 1 astronomical unit, or AU, and it becomes our measuring stick for the solar system. Now, let's venture outward to where things become genuinely alien to human experience. Pluto, at its farthest point from the Sun, orbits at about 49 AU. All Voyager spacecraft, humanity's most distant ambassadors, have traveled roughly 150 AU from the Sun after more than 4 decades of journey. These distances already stretch our comprehension, but they represent merely the opening notes in the symphony of cosmic scale. The inner edge of the Oort Cloud begins at approximately 2000 AU from the Sun. To put this in perspective, if Earth's orbit were the size of a quarter, the inner Oort Cloud would begin at a distance of roughly 50 feet. Light from the Sun takes about 11 days to reach the inner Oort Cloud. Imagine shouting toward the edge of our solar system and having to wait 11 days just for your voice to arrive. But we're only beginning our journey into the abyss. The outer reaches of the Oort Cloud extend to distances of 100,000 to 200,000 AU from the Sun. At these distances, sunlight takes nearly 3 years to make the journey from our star to the edge of its gravitational domain. We are approaching distances measured in light years, the scale typically reserved for the spaces between stars. Here's where the numbers become truly mind-bending. 1 light year equals about 63,000 AU. The outer Oort Cloud extends to roughly 3 light years from the Sun, which means our solar system's boundary reaches 3/4 of the way to the nearest star. This isn't just large, this is cosmically enormous. Our solar system occupies a sphere of space nearly 6 light-years across, with the vast majority of this volume consisting of the invisible, empty darkness of the Oort Cloud. To grasp this scale, imagine shrinking our solar system until Earth's orbit around the Sun becomes the size of a basketball. On this scale, Pluto's orbit would extend out to about 200 feet. The inner Oort Cloud would begin at roughly 2 miles from the basketball, while the outer edge would extend to 100 miles away. Picture standing with your basketball-sized solar system and realizing that its true boundary lies beyond the horizon, farther than you could walk in a day. The volume of space enclosed by the Oort Cloud is staggering. If the 8 planets and all the asteroids in our solar system were compressed into a single sphere, that sphere would have a diameter of roughly 12,000 miles, smaller than Earth. The Oort Cloud, by contrast, occupies a volume of space roughly 15 billion times larger than the volume enclosed by Neptune's orbit. It's as if our familiar solar system, planets, moons, asteroids and all, exists as a tiny dense kernel at the center of an enormous sphere of cosmic emptiness. This vast scale creates what astronomers call the cosmic loneliness problem. Within the Oort Cloud's enormous volume, an estimated 1 trillion objects drift in isolation. That sounds like a lot until you realize that these trillion objects are scattered across a volume of space so vast that the average distance between neighboring objects is millions of miles. If you could somehow stand on an Oort Cloud object, the nearest neighbor would likely be invisible, lost in the cosmic darkness at a distance greater than the diameter of our Sun. The scale of this emptiness defies human experience. In our everyday lives, we're accustomed to spaces that are either full of matter or relatively small when empty. The Oort Cloud represents something alien to terrestrial experience, a volume of space larger than some stellar systems, occupied by objects so sparse and distant that they might as well not exist. This cosmic emptiness is not just a curiosity, it's the fundamental reason why the Oort Cloud remains invisible to us. When objects are separated by distances measured in millions of miles and scattered across a volume measured in light years, the very concept of density becomes meaningless. Ivitogrotas, and every concept of density becomes meaningless. We're not just looking for needles in a haystack, we're looking for invisible needles in a haystack the size of multiple solar systems. The scale of the Oort Cloud forces us to confront the reality that our solar system is not the compact, well-defined neighborhood we imagine it to be, but rather a vast wilderness of cosmic emptiness punctuated by occasional islands of matter drifting in eternal darkness. There comes a point in our cosmic neighborhood where our Sun's authority begins to wane, where its gravitational grip weakens, and where the influence of distant stars and the galaxy itself begins to compete for dominance. This boundary, invisible but real, marks the true edge of our solar system and the limit of the Sun's cosmic kingdom. The Sun's gravitational influence extends far beyond the orbit of Pluto, far beyond even the Kuiper belt where Pluto resides. But gravity, like light, follows the inverse square law. Its strength diminishes with the square of distance. At the distances of the Oort Cloud, our Sun's gravitational pull becomes so weak that it barely exceeds the gravitational tug of nearby stars and the collective pull of our entire galaxy. Imagine our Sun as a cosmic lighthouse, its gravitational beacon reaching outward into space. Close to the Sun, this beacon is strong and unwavering, holding planets in stable, predictable orbits. But as we venture outward toward the Oort Cloud, the beacon begins to flicker and fade. Other lighthouses, distant stars begin to compete for attention, their gravitational signals mixing with our Sun's weakening influence. At the outer edge of the Oort Cloud, roughly 100,000 to 200,000 AU from the Sun, objects orbit so slowly that they complete one revolution around our star every few million years. Their orbital velocities are measured in meters per second rather than kilometers per second, slower than a walking pace. At these distances, the Sun's gravity is so weak that passing stars can permanently steal objects from our solar system or inject new ones into our cosmic neighborhood. This creates what astronomers call the zone of gravitational confusion, a region where objects nominally belong to our solar system, but are so weakly bound to the Sun that their ultimate fate depends on the gravitational whims of passing cosmic neighbors. It's as if the outer Oort cloud exists in a state of gravitational limbo, neither fully committed to our Sun nor entirely free from its influence. The boundary becomes even more complex when we consider the role of the Milky Way galaxy itself. Our entire solar system orbits the galactic center, completing one revolution every 225 million years. This galactic motion creates tidal forces that stretch and compress the outer solar system, much like how the moon's gravity creates tides on Earth's oceans. These galactic tides become significant factors in the outer Oort cloud, competing with the Sun's gravity to shape the orbits of distant objects. There's also the influence of what astronomers call the galactic plane, the disk of stars, gas and dust that defines our galaxy's main structure. As our solar system oscillates above and below this galactic plane during its 225 million year orbit, objects in the outer Oort cloud experience varying gravitational influences. Sometimes they're pulled toward the dense galactic disk, other times they're relatively free from galactic influence. This creates a dynamic boundary that changes over millions of years. The effective edge of our solar system, the point where the Sun's gravity can no longer hold objects in orbit, expands and contracts based on our position relative to other stars and our location within the galaxy. It's a breathing boundary, a flexible edge that responds to the cosmic environment around us. The practical result is that the outer Oort cloud represents not just the edge of visibility, but the edge of gravitational allegiance. Objects there exist in a twilight realm where they might belong to our solar system for a few million years before being captured by a passing star or ejected into interstellar space by galactic tides. This gravitational boundary helps explain why we cannot see past the Oort cloud. Beyond this region, any objects that might exist would not truly belong to our solar system. They would be interstellar wanderers, rogue planets or asteroids, drifting through the space between stars, too distant and too disconnected from our Sun to be considered part of our cosmic family. The dying influence of our Sun's gravity marks not just a physical boundary, but a conceptual one, the point where our solar system ends and the vast wilderness of interstellar space begins. In 1977, when disco ruled the airwaves and the Cold War dominated headlines, humanity launched two small spacecraft on what would become the most ambitious reconnaissance mission in our species' history. The Voyager probes, each weighing less than a small car, were originally designed for a simple 4-year tour of the outer planets. Nearly half a century later, they continue to transmit data from the edge of interstellar space, but their journey toward the Oort cloud has barely begun. To understand the magnitude of the Voyager mission and why it represents both humanity's greatest step into the cosmic darkness and a sobering reminder of our limitations, we need to appreciate what these robotic explorers have accomplished and how far they still have to go. Voyager 1, currently our most distant human-made object, has traveled approximately 14.8 billion miles from Earth, roughly 159 times the distance from Earth to the Sun. This sounds impressively far, until you realize that it represents less than 0.08% of the distance to the inner edge of the Oort cloud. If the journey to the Oort cloud were a cross-country road trip from New York to Los Angeles, Voyager 1 would have traveled roughly the length of a city block. The numbers become even more humbling when we consider time. Voyager 1 has been traveling for over 45 years to reach its current position. At its current speed of about 38,000 miles per hour relative to the Sun, it would take approximately 300 years to reach the inner edge of the Oort cloud, and roughly 30,000 years to traverse the entire Oort cloud region. To put this in historical perspective, when Voyager 1 finally reaches the inner Oort cloud, more time will have passed than the entire recorded history of human civilization. But here's the cruel reality. Voyager 1's nuclear power source is already failing. The spacecraft's electricity comes from radioisotope thermoelectric generators, RTGs, that convert the heat from decaying plutonium into electrical power. These RTGs lose about 4 watts of power each year, and NASA estimates that by 2025, there won't be enough power to operate any of the scientific instruments. The spacecraft will continue its journey into the darkness, but it will do so in silence, no longer able to tell us what it encounters. Even if Voyager 1 could somehow continue transmitting data for centuries, it faces another fundamental challenge. It's heading in the wrong direction to encounter the bulk of Oort Cloud objects. The spacecraft is traveling roughly toward the constellation Ophiuchus, but Oort Cloud objects are distributed spherically around the Sun. The probability that Voyager 1 will actually encounter an Oort Cloud object during its multi-thousand-year journey is virtually zero, like shooting an arrow randomly into the sky and hoping to hit a specific bird. Voyager 2, currently about 12.4 billion miles from Earth, faces similar limitations. While it took a different trajectory and provided us with spectacular images of Uranus and Neptune, it too is running out of power and heading into a region of space where encounters with Oort Cloud objects are statistically negligible. The Voyager missions highlight a fundamental challenge in exploring the outer solar system. The sheer scale involved makes traditional spacecraft missions almost meaningless. These probes, which revolutionized our understanding of the giant planets and first crossed into interstellar space, become insignificant dots in the vast emptiness of the Oort Cloud region. Yet the Voyager mission has provided us with invaluable data about the boundary regions of our solar system. In 2012, Voyager 1 became the first human-made object to cross the heliopause, the boundary where the solar wind meets interstellar space. This achievement marked humanity's first direct sampling of the interstellar medium, the thin soup of gas and particles that fills the space between stars. The data from this historic boundary crossing revealed surprises that have implications for understanding the Oort Cloud. The interstellar magnetic field proved to be stronger than expected, and the density of interstellar particles was higher than models predicted. This information helps us understand the environment in which Oort Cloud objects exist, a region where solar influence wanes and interstellar forces begin to dominate. Voyager's journey also demonstrated the profound isolation of interstellar space. As the spacecraft crossed the heliopause, it entered a region where the familiar solar wind, the stream of charged particles flowing from our Sun, gives way to the cosmic radiation of interstellar space. Voyager's journey also demonstrated the profound isolation of interstellar space. This transition marks the beginning of true cosmic loneliness, a realm where objects exist in the influence of distant stars rather than our Sun. The most poignant aspect of the Voyager mission may be its golden records, phonograph records, containing sounds and images from Earth, intended as messages to any extraterrestrial intelligence that might encounter the spacecraft. These records will likely outlast human civilization, continuing their journey through the galaxy long after Earth itself has been consumed by the Sun's eventual expansion into a red giant star. Carl Sagan, one of the architects of the Voyager mission, described the spacecraft as a kind of time capsule intended to communicate to extraterrestrials a story of our world. But in the context of the Oort Cloud, the Voyagers also represent something else: humanity's first tentative steps into a realm so vast and empty that our most ambitious efforts barely register as movement. The Voyager missions force us to confront the reality of cosmic distances. These spacecraft, humanity's fastest and most distant emissaries, will spend thousands of years crossing a region we cannot see and cannot directly study. They represent both the triumph of human ingenuity and the humbling reality of our cosmic limitations. As Voyager 1 continues its silent journey into the darkness beyond the heliopause, it carries with it not just scientific instruments and golden records, but humanity's first physical presence in the realm where the Oort Cloud begins. Yet this presence is so minuscule, so lost in the vast emptiness of interstellar space, that it might as well be invisible, a fitting metaphor for our relationship with the cosmic boundary we cannot see. The limitations of the Voyager missions have not deterred mission planners from dreaming of future expeditions to the outer solar system. But every proposed mission to study the Oort Cloud region faces the same unforgiving mathematics of distance, time, and energy that have defined space exploration since its beginning. NASA and other space agencies have proposed various concepts for what they call interstellar precursor missions, spacecraft specifically designed to venture into the region where the Oort Cloud begins. These missions represent some of the most ambitious engineering challenges ever conceived, requiring technologies that push the boundaries of what's currently possible. The most promising concept involves spacecraft powered by nuclear electric propulsion, using small nuclear reactors to generate electricity that powers ion drives. These spacecraft could theoretically achieve speeds of 200,000 to 300,000 miles per hour, roughly 5 to 7 times faster than Voyager. Even at these unprecedented speeds, a mission to the inner Oort Cloud would require 50 to 70 years of travel time. A complete traverse of the Oort Cloud would still take several centuries. But speed is only part of the challenge. Any spacecraft venturing into the Oort Cloud region must be designed to operate autonomously for decades or centuries, far beyond the lifespan of the engineers who built it. Current spacecraft electronics typically function for 10 to 20 years before degrading beyond usefulness. Designing systems that can operate reliably for 50 to 100 years represents an engineering challenge that hasn't been solved. The European Space Agency has proposed the Interstellar Express mission concept, which would use a combination of solar sails and gravity assists to achieve extreme velocities. By using the sun's radiation pressure and carefully planned gravitational slingshots around multiple planets, such a spacecraft might reach speeds approaching 500,000 miles per hour. Even at this fantastic velocity, the journey to the inner Oort Cloud would require 25 to 30 years. Perhaps the most ambitious concept is NASA's Breakthrough Starshot initiative, which proposes using powerful lasers to accelerate tiny spacecraft 100 to 20% the speed of light. These spacecraft, each weighing only a few grams, could theoretically reach the Oort region in just a few years. However, at such enormous speeds, they would cross the entire Oort Cloud in a matter of hours, providing only a brief snapshot of conditions there. The communication challenges for Oort Cloud missions are equally daunting. Radio signals from the inner Oort Cloud would take 11 days to reach Earth at the speed of light. From the outer Oort Cloud, signals would require nearly 3 years to make the journey home. This means that any spacecraft exploring these regions would need to operate with complete autonomy, making decisions and conducting experiments without any possibility of real-time guidance from Earth. Power generation presents another seemingly insurmountable obstacle. Solar panels become virtually useless at Oort Cloud distances, where sunlight is millions of times weaker than at Earth. Nuclear power sources face their own limitations. The plutonium-238 used in current RTGs has a half-life of 88 years, meaning that power output decreases significantly over the multi-decade journey times required. Some mission concepts propose hybrid approaches, combining multiple exploration strategies. Networks of small probes could be scattered throughout the inner solar system using gravitational microlensing to detect Oort Cloud objects as they pass in front of background stars. Space-based telescopes positioned at the outer edge of the planetary region could potentially spot the largest Oort Cloud objects through careful, long-term observations. Hindi wajah saamin siri alview mentor but TIB. The most realistic near-term missions focus not on reaching the Oort Cloud itself, but on studying its effects and boundaries. The proposed interstellar probe mission, currently in development phases, would travel to approximately 1,000 AU from the Sun, still far short of the Oort Cloud, but deep enough into interstellar space to study the environment where Oort Cloud objects exist. These future missions face not just technical challenges, but also sociological ones. Any mission to the Oort Cloud region would span multiple human generations. The scientists who design and launch such missions would likely not live to see the results. This requires a level of long-term commitment and institutional continuity that challenges traditional approaches to space exploration. The financial implications are equally staggering. Current estimates for interstellar precursor missions range from tens to hundreds of billions of dollars, making them among the most expensive scientific endeavors ever proposed. The cost per bit of data returned from the Oort Cloud region would be astronomical, raising questions about whether such missions represent the best use of limited resources for space exploration. Despite these challenges, the scientific community continues to develop concepts for Oort Cloud exploration, because the potential discoveries could revolutionize our understanding of solar system formation, planetary migration, and the frequency of planetary systems in the galaxy. The Oort Cloud represents a fossil record of the early solar system, preserving materials and conditions from the era when planets were forming. The century-long wait for meaningful data from the Oort Cloud region represents perhaps the ultimate test of human patience and scientific commitment. It forces us to think beyond individual careers, beyond single generations, and toward a model of scientific exploration that spans centuries rather than decades. Our solar system does not exist in isolation. It drifts through space in a cosmic neighborhood populated by hundreds of nearby stars, each one a gravitational giant capable of reaching across the light years to disturb the delicate architecture of our outer solar system. These stellar neighbors create a gravitational chaos that makes the Oort Cloud not just invisible, but dynamically unstable. Every 26 million years or so, our solar system passes through the densest regions of the Milky Way's spiral arms, regions packed with massive stars and stellar remnants. During these passages, the gravitational environment around our solar system becomes turbulent, however, with multiple stars passing within a few light years of our cosmic neighborhood. Each close encounter acts like a cosmic storm, stirring the Oort Cloud and fundamentally altering its structure. Consider what happens when a star passes within 1 or 2 light years of our solar system, an event that occurs roughly every million years. At Oort Cloud distances, where our sun's gravitational influence is already weak, the gravitational pull of a passing star can be comparable to, or even stronger than, our sun's hold on distant objects. This creates a cosmic tug-of-war, with objects in the outer Oort Cloud pulled between competing gravitational masters. The mathematics of these stellar encounters reveal their devastating effects on Oort Cloud visibility. Computer simulations show that a typical stellar flyby can eject roughly 90% of objects from the outer Oort Cloud, flinging them into interstellar space, where they become rogue planets and asteroids wandering between the stars. The remaining 10% get their orbits so severely disrupted that they either plunge toward the inner solar system as long-period comets, or get redistributed into completely different regions of the Oort Cloud. These disruptions explain one of the great mysteries of the Oort Cloud, why we see relatively few long-period comets, despite theoretical models suggesting the Oort Cloud should contain trillions of objects. The answer lies in the destructive influence of passing stars, which have spent the last 4.6 billion years systematically stripping away and redistributing the outer solar system's population. But stellar encounters don't just remove objects from the Oort Cloud, they also add new ones. When stars pass close to our solar system, they can capture objects from their own Oort clouds and inject them into ours. This means that some of the objects we consider part of our solar system may actually be interstellar immigrants, adopted from other stellar systems during ancient gravitational encounters. The most famous example of this stellar disruption involves Schultz's star, a red dwarf system that passed within 0.8 light-years of our solar system, approximately 70,000 years ago. This recent encounter, recent in astronomical terms, likely sent a shower of comets from the outer Oort cloud toward the inner solar system. Some of these comets may still be en route, destined to appear in Earth's skies thousands of years from now, as spectacular visitors bearing messages from our stellar encounter. The gravitational influence of nearby stars creates what astronomers call stellar tidal forces throughout the Oort cloud region. These forces are subtle but persistent, gradually reshaping orbits over millions of years, even without direct stellar encounters. The cumulative effect is to create a constantly changing gravitational landscape where objects in the outer Oort cloud never experience stable, predictable conditions. This stellar interference compounds the visibility problem in ways that go beyond simple gravitational disruption. When stellar encounters redistribute Oort cloud objects, they scatter them across even larger volumes of space, reducing their already negligible density to virtually zero. It's as if the cosmic storms caused by passing stars take an already sparse population and spread it even thinner across the vast darkness. The timing of stellar encounters also creates observational challenges that span geological timescales. The comets we observe today may be the result of stellar encounters that occurred millions of years ago, when early humans were just beginning to walk upright. Meanwhile, the stellar encounters happening now will send their comet showers toward the inner solar system millions of years in the future, long after our current civilization has become archaeological curiosity. Perhaps most significantly, stellar interference means that the Oort cloud we're trying to observe may not represent a stable, permanent structure at all, but rather a temporary snapshot of objects caught between stellar influences. The Oort cloud may be better understood as a dynamic region where objects from multiple stellar systems mix, interact, and exchange, creating a gravitational melting pot that spans multiple light years. This realization forces us to reconsider what we mean when we talk about the boundary of our solar system. If objects in the outer Oort cloud are constantly being exchanged with other stellar systems, then the true edge of our solar system becomes not a fixed boundary, but a fluid, ever-changing zone of gravitational influence that expands and contracts based on the cosmic traffic in our galactic neighborhood. The interference from other stars transforms the Oort cloud from a simple observational challenge into a fundamental question about the nature of gravitational territories in space and the permanence of the structures we call solar systems. Beyond the disruptive influence of individual stars lies an even more profound force shaping the invisible architecture of the Oort cloud, the gravitational tide of the entire Milky Way galaxy. This cosmic tide, subtle but unrelenting, represents the collective gravitational pull of 100 billion stars working together to stretch, compress, and reshape the outer boundary of our solar system. Our solar system orbits the center of the Milky Way at a distance of roughly 26,000 light-years, completing one galactic revolution every 250 million years. This orbital motion creates a complex gravitational environment where our solar system experiences varying tidal forces as it moves through different regions of the galaxy. Sometimes we're in the sparse regions between spiral arms. Other times we plunge through the dense stellar neighborhoods of the galactic disk. The galactic tide operates like a cosmic version of the tidal forces that Earth's moon exerts on our oceans, but on an incomprehensibly larger scale. Just as the moon's gravity pulls more strongly on the side of Earth closest to it, creating tidal bulges in our oceans, the galaxy's gravity pulls more strongly on the side of the gentle Oort cloud closest to the galactic center. This differential gravitational pull stretches the Oort cloud into an elongated shape, with objects on the galactic side experiencing stronger gravitational acceleration than those on the opposite side. This galactic stretching creates what astronomers call the galactic tide limit, a boundary beyond which our sun cannot maintain gravitational control over objects in its Oort cloud. Zorgidlai dortarari, with the tired bashda, objects beyond this limit get stripped away by galactic tidal forces and become part of the general interstellar population. Current calculations suggest this limit lies at approximately 100,000 to 200,000 AU from the Sun, effectively defining the maximum possible extent of our solar system. But the galactic tide doesn't just set boundaries, it actively sculpts the distribution of objects within the Oort cloud. Computer models show that galactic tidal forces create preferential directions for object orbits, concentrating Oort cloud objects along certain orientations while depleting others. This creates a lumpy asymmetrical structure rather than the smooth spherical shell that early models predicted. The influence becomes even more complex when we consider that our solar system oscillates above and below the galactic plane like a cosmic yo-yo, completing one up and down cycle every 60 to 70 million years. During periods when we're moving through the dense galactic disk, tidal forces intensify, stripping away more objects from the outer Oort cloud and sending showers of comets toward the inner solar system. Some researchers have proposed that these passages through the galactic plane correlate with mass extinction events on Earth, as increased comet activity brings with it the possibility of large impact events. While this galactic extinction hypothesis remains controversial, it highlights how the galactic tide's influence on the Oort cloud can have consequences that ripple all the way down to life on Earth. The galactic tide also interacts with the disruptive effects of passing stars to create what scientists call compound gravitational chaos. When stellar encounters occur during periods of strong galactic tidal influence, their disruptive effects become amplified. Objects already weakened by galactic tidal forces are more easily stolen by passing stars or ejected into interstellar space. This hidden galactic hand shapes not just the structure of our Oort cloud, but our ability to observe it. The constant reshaping and depletion caused by galactic tides means that the Oort cloud we're trying to study represents only a fraction of the objects that originally formed in this region. This region, the majority have been stripped away over the 4.6 billion-year history of our solar system, leaving behind a sparse remnant population scattered across vast volumes of space. This region, perhaps most remarkably, the galactic tide connects our solar system's invisible boundary to the large-scale structure of the entire galaxy. The same gravitational forces that shape spiral arms and control the orbits of stars also reach down to influence the distribution of icy objects in our outer solar system. The Oort cloud thus becomes not just a feature of our local cosmic neighborhood, but a participant in galactic-scale dynamics that span hundreds of thousands of light-years. At the boundary of the Oort cloud, we encounter something far more profound than a simple observational limit. Here, at the edge of our solar system's gravitational influence, the very foundations of knowledge, reality, and existence intersect in ways that challenge our most basic assumptions about what it means to know something and what constitutes the boundary between the real and the unknowable. The question, why can't we see past the Oort cloud, initially appears to have straightforward scientific answers: insufficient light, vast distances, the inverse square law, and technological limitations. But as we dig deeper into this cosmic mystery, we discover that we're really asking something much more fundamental. What defines the boundary between what exists and what we can confirm exists? Consider the philosophical implications of the Oort cloud's invisibility. Here we have a structure that theory predicts must exist, mathematics proves should be there, and physics requires to explain observable phenomena, yet it remains beyond direct detection. This creates what philosophers of science call an evidential paradox. Our best scientific methods tell us something is real, while our best observational tools tell us it's non-existent. The German philosopher Immanuel Kant distinguished between the phenomenal world, the world as we perceive it through our senses and instruments, and the noumenal world, the world as it actually exists, independent of our observation. The Oort cloud represents a perfect example of this distinction. In the phenomenal world, it doesn't exist because we cannot observe it. In the noumenal world, it must exist because the alternative violates physical law. This philosophical tension becomes even more complex when we consider the role of inference in scientific knowledge. Everything we know about the Oort cloud comes from indirect evidence: the orbital characteristics of long-period comets, computer simulations of solar system formation, and mathematical models of gravitational interactions. We have constructed an elaborate theoretical edifice to describe something we have never seen, touched, or directly detected in any way. The epistemological questions multiply when we consider the temporal aspects of Oort cloud invisibility. Many of the comets we observe today began their journeys from the Oort cloud thousands or millions of years ago. We're seeing evidence of the Oort cloud's past state, not its present condition. The objects we infer must exist in the Oort cloud today exist in our present only as mathematical extrapolations from ancient evidence. In what sense can we claim to know about something that exists in a present we cannot observe? based on evidence from a past we can only infer. The boundary of observability, represented by the Oort Cloud, also forces us to confront the relationship between physical reality and human consciousness. The vast majority of our solar system exists in a realm beyond human perception, operating according to physical laws, but never intersecting with human experience, except through the occasional comet visitor. This raises profound questions about the role of consciousness in defining reality. Does a trillion-object structure that never enters human awareness truly exist in any meaningful sense? Some interpretations of quantum mechanics suggest that observation itself plays a fundamental role in defining reality, that objects exist in probabilistic states until they are observed and measured. While this interpretation is controversial and typically applied only to quantum-scale phenomena, the Oort Cloud presents us with a classical-scale version of the same paradox. A vast structure that exists in a state of permanent non-observation, never collapsing from theoretical probability into observational reality. The invisibility of the Oort Cloud also highlights what philosophers call the problem of other minds extended to cosmic scales. Just as we can never directly observe another person's consciousness, but must infer its existence from external behaviors, we cannot directly observe the Oort Cloud, but must infer its existence from the behavior of comets and the mathematics of orbital mechanics. In both cases, we're making fundamental assumptions about unobservable realities based on observable effects. This leads us to consider whether the boundary of the Oort Cloud represents what philosophers call an epistemic horizon, a fundamental limit to possible knowledge, rather than merely a technological or observational challenge. If the inverse square law and the vast distances involved ensure that Oort Cloud objects remain forever beyond direct observation, regardless of technological advances, then we may have encountered not just a practical limit, but a theoretical one, a boundary beyond which knowledge itself becomes impossible. This epistemic horizon forces us to reconsider the relationship between scientific truth and observational verification. The scientific method has traditionally relied on the principle that theories must be testable and falsifiable through observation or experimentation. But the Oort Cloud challenges this paradigm by being simultaneously necessary for our understanding of physics and permanently beyond the reach of direct verification. The philosopher Karl Popper argued that scientific theories gain their validity not from being proven true, but from being potentially disprovable, falsifiable. Yet how can we falsify the existence of something we cannot observe? The Oort Cloud exists in a peculiar logical space where it cannot be conclusively proven to exist, but its non-existence would falsify our understanding of gravitational mechanics, solar system formation, and comet dynamics. This creates what we might call the paradox of necessary invisibility. The Oort Cloud must exist for our physics to be correct, but its very existence ensures that it cannot be directly observed. We find ourselves in the strange position of being most confident about the reality of something we cannot see, precisely because we cannot see it. The philosophical implications extend even further when we consider the nature of scientific explanation itself. Science traditionally progresses by replacing invisible theoretical entities with observable, measurable ones. We replace the invisible humors of ancient medicine with observable bacteria and viruses. Science, we replace the invisible aether of 19th century physics with the observable electromagnetic spectrum. But the Oort Cloud represents a reversal of this pattern, a scientific entity that becomes more theoretically necessary as our observational capabilities improve, yet remains permanently invisible. This leads us to a profound question about the limits of human knowledge. Are there aspects of reality that are, by their very nature, permanently beyond human comprehension? The Oort Cloud suggests that the answer might be yes, not because we lack intelligence or technology, but because the fundamental structure of physics itself creates boundaries beyond which knowledge cannot pass. The invisibility of the Oort Cloud also raises questions about the nature of existence itself. If something has physical effects, if it influences the orbits of comets, shapes the dynamics of our solar system, and plays a crucial role in the cosmic ecosystem, but never enters human consciousness except as mathematical abstraction. In what sense does it exist? This question touches on ancient philosophical debates about the relationship between being and knowing, between ontology and epistemology. Perhaps most profoundly, the Oort Cloud forces us to confront the possibility that human beings, for all our scientific achievements and technological capabilities, remain fundamentally local creatures in a cosmic sense. We can send our instruments to the edge of the solar system. We can detect galaxies billions of light years away, but we cannot directly observe the boundary of our own cosmic neighborhood. This locality isn't just a current limitation. It may be a permanent feature of conscious existence in a universe governed by the inverse square law. The philosophical weight of the Oort Cloud's invisibility ultimately leads us to a humbling realization. The universe contains vast realms of reality that exist beyond the boundaries of possible human experience. These realms are not supernatural or mystical. They operate according to well-understood physical laws, but they are forever separated from human consciousness by the mathematics of distance and light. This separation challenges our anthropocentric view of knowledge and existence. We are forced to accept that the universe is not primarily designed for human understanding, that there are aspects of reality that exist not for us to discover, but simply because the laws of physics require them to exist. The Oort Cloud represents a cosmic lesson in intellectual humility, a reminder that the boundaries of human knowledge are not merely technological limitations to be overcome, but fundamental features of existence in a universe far larger and more mysterious than human consciousness can fully comprehend. In confronting the invisible boundary of the Oort Cloud, we are really confronting the limits of what it means to be conscious, observing beings in a cosmos that extends far beyond the reach of any possible observation. Beyond the Oort Cloud lies a realm that challenges our very conception of emptiness, the interstellar medium, cosmic ocean of gas, dust, and particles, so tenuous that it makes the best laboratory vacuum seem dense by comparison, yet so vast that it contains more matter than all the stars in our galaxy combined. This interstellar ocean is where the Oort Cloud makes its home, suspended not in true emptiness, but in a dilute soup of atoms and molecules that tells the story of stellar death and cosmic recycling. Understanding this medium is crucial to grasping why the boundary of our solar system remains invisible, because the interstellar medium doesn't just provide the backdrop for the Oort Cloud. It actively interacts with it, shapes it, and ultimately helps determine what we can and cannot observe. The density of the interstellar medium averages roughly 1 atom per cubic centimeter, a vacuum so perfect that it would be impossible to create in any Earth-based laboratory. To put this in perspective, the air you're breathing contains approximately 27 billion molecules per cubic centimeter. The interstellar medium is so empty that if you could somehow gather all the matter in a cube of space, 1 light year on each side, you would collect only enough material to make a few dozen snowballs. Yet this near-perfect vacuum contains secrets that reveal themselves through spectroscopic analysis. The interstellar medium consists primarily of hydrogen, the universe's most abundant element, along with traces of heavier elements forged in the nuclear furnaces of dying stars. Oxygen, carbon, nitrogen, and iron drift through this cosmic ocean as individual atoms or simple molecules, many of them ionized by the radiation from nearby stars. Temperature in the interstellar medium varies dramatically depending on local conditions, ranging from near absolute zero in the coldest, densest regions to millions of degrees in areas heated by stellar winds and supernova explosions. This temperature variation creates a complex, turbulent environment where hot and cold regions mix in ways that influence how matter moves through space and how electromagnetic radiation propagates across vast distances. The interstellar medium also contains dust grains, tiny particles of silicates, carbon, and ice that are crucial for understanding Oort Cloud visibility. These microscopic particles, typically smaller than the wavelength of visible light, scatter and absorb electromagnetic radiation in ways that create what astronomers call interstellar extinction. Over the vast distances to the Oort Cloud, even the minimal dust content of the interstellar medium becomes significant, further dimming objects that are already at the limits of observability. But perhaps the most fascinating aspect of the interstellar medium is its role as a cosmic recycling system. The atoms and molecules drifting through this space are not primordial. They are the processed remains of previous generations of stars. The carbon in interstellar dust grains was forged in the cores of ancient red giants. The oxygen was created in massive stars that ended their lives as supernovae. The iron atoms scattered through this medium were synthesized in the final moments before stellar collapse. This cosmic recycling has profound implications for understanding the Oort Cloud region. The objects in the Oort Cloud formed from materials that condensed out of the interstellar medium during the early phases of solar system formation, 4.6 billion years ago. In a very real sense, the Oort Cloud objects are made from interstellar medium that has been temporarily captured and organized by our sun's gravity, but they exist in an environment that remains essentially interstellar in character. The boundary between the solar system and the interstellar medium is not sharp but gradual, marked by the heliopause, where the solar wind meets the interstellar wind. The Voyager spacecraft have provided our first direct measurements of conditions beyond this boundary, revealing that the interstellar medium has properties significantly different from theoretical predictions. The magnetic field strength is higher than expected, and the density of neutral atoms is greater than models suggested. These discoveries have implications for understanding Oort cloud dynamics. The interstellar medium exerts drag on objects moving through it, gradually changing their orbits over millions of years. More significantly, variations in the density and composition of the interstellar medium as our solar system moves through the galaxy create changing environmental conditions that influence the structure and evolution of the Oort cloud. The interstellar medium also serves as a communication channel for cosmic events. Shock waves from distant supernovae propagate through this medium, carrying energy and momentum that can disturb objects in the outer Oort cloud. The compression and expansion of the interstellar medium as our solar system moves through different galactic environments creates pressure waves that influence the distribution of objects at our system's edge. Understanding the interstellar medium forces us to recognize that the Oort cloud doesn't exist in isolation, but as part of a vast dynamic galactic ecosystem. The invisible boundary of our solar system is not a fixed edge, but a fluid interface between solar and interstellar influences, constantly shifting as our entire solar system moves through the galaxy's varying interstellar environment. We stand at a profound crossroads in human understanding, where the boundaries of what we can observe intersect with the boundaries of what actually exists. The Oort cloud represents more than just an astronomical curiosity. It embodies the fundamental tension between the universe as it truly is and the universe as we are capable of perceiving it. Throughout human history, we have gradually expanded our observational reach. We discovered microscopic organisms invisible to the naked eye. We detected radio waves from distant galaxies and photographed the cosmic microwave background radiation left over from the Big Bang itself. Each technological advance pushed back the boundaries of the observable universe, revealing new layers of reality that had previously remained hidden. But the Oort cloud presents us with a different kind of boundary. Not one that technology can eventually overcome, but one that appears to be fundamental and permanent. The inverse square law ensures that no matter how advanced our telescopes become, objects at Oort cloud distances will remain effectively invisible, lost in the mathematical inevitability of diminishing light. This creates what we might call the great cosmic irony. We can observe galaxies billions of light years away, witness the birth and death of stars in distant regions of the universe, and detect planets orbiting alien suns. Yet we cannot see the boundary of our own cosmic neighborhood. The most distant quasar is more visible to us than the nearest Oort cloud object. This irony reveals something profound about the nature of reality and observation. The universe we can observe, what cosmologists call the observable universe, is not necessarily the same as the universe that actually exists. Beyond our observational horizon lie realms of reality that operate according to physical laws but remain forever separated from human experience. The distinction between the observable and the real becomes even more complex when we consider that the Oort Cloud's invisibility is not absolute but contextual. These objects are invisible to us from our location and with our physical limitations, but they would be perfectly visible to a hypothetical observer located closer to them or equipped with different sensory capabilities. Reality itself doesn't change, only our access to it. This raises uncomfortable questions about the role of observation in defining scientific truth. The scientific method has traditionally relied on the principle that theories must be testable through observation or experimentation. But what happens when fundamental physical laws prevent certain aspects of reality from ever being directly observed? Does unobservable reality truly count as scientific knowledge? The Oort Cloud forces us to expand our definition of scientific evidence beyond direct observation to include mathematical necessity, logical inference, and consistency with established physical principles. We accept the reality of the Oort Cloud not because we can see it, but because its non-existence would violate everything we understand about physics, orbital mechanics, and solar system formation. This represents a profound shift in how we think about knowledge and reality. We are acknowledging that there are aspects of the universe that are real, that have physical effects and influence observable phenomena, but that remain permanently beyond direct human experience. The boundaries of human knowledge are not just technological limitations to be overcome, but fundamental features of existence in a universe governed by physical laws. The observable versus real distinction also highlights the parochial nature of human perspective. We tend to think of the universe in terms of what we can see, detect, and measure, but the reality is that the vast majority of the universe exists beyond our observational horizon. We are local creatures in a cosmic sense, able to directly experience only the tiniest fraction of what actually exists. Perhaps most significantly, the Oort Cloud teaches us that reality does not require human observation to exist. The trillion objects drifting in the cosmic darkness beyond our sight are not waiting for us to discover them in order to become real. They exist, whether we acknowledge them or not, following physical laws and participating in cosmic processes, completely independent of human consciousness. This lesson in cosmic humility forces us to accept that the universe was not designed for human understanding, but there are vast realms of reality that exist not for us to discover, but simply because the laws of physics require them to exist. As we reach the end of our journey to the invisible boundary of our solar system, we must confront the most profound question of all. What does the existence of unobservable reality tell us about our place in the cosmos and the nature of existence itself? The Oort Cloud represents something unprecedented in the history of human knowledge, a structure that is simultaneously central to our understanding of the solar system and completely beyond our ability to directly observe. This paradox reveals fundamental truths about the relationship between consciousness and cosmos, between knowing and being, that challenge our most basic assumptions about reality. Consider the implications of living in a universe where the majority of our own cosmic neighborhood remains forever hidden from view. Every night, when we look up at the stars, we are seeing only the illuminated exceptions in a universe dominated by darkness. The photons reaching our eyes represent a vanishingly small fraction of what actually exists. Most of reality dwells in the invisible spaces between the lights. This cosmic darkness is not empty. It is full of structure, process, and meaning that unfolds without any requirement for human observation or understanding. In the Oort Cloud, objects follow complex orbital patterns, respond to gravitational influences from passing stars, and participate in the cosmic recycling of matter across billions of years. This hidden reality has its own history, its own evolutionary processes, its own intricate relationships, all occurring in a realm beyond human perception. The existence of such vast, unobservable structures forces us to confront our cosmic loneliness in new ways. We often imagine that advancing technology will gradually reveal all cosmic secrets, that eventually human knowledge will encompass all of reality. But the Oort Cloud teaches us that there will always be realms beyond our reach, not because of technological limitations, but because of the fundamental structure of physics itself. This permanent inaccessibility of vast cosmic regions carries profound philosophical implications. If reality extends far beyond what can ever be observed, then the universe is not primarily about consciousness, intelligence, or knowledge. It is about existence itself, independent of any observer. The cosmos operates according to principles that do not require validation through observation or understanding through consciousness. Yet there is something almost miraculous about the fact that we can deduce the existence of invisible realms through mathematics, logic, and scientific reasoning. While we cannot see the Oort cloud directly, we can map its structure through mathematical models, predict its behavior through computer simulations, and understand its role in the cosmic ecosystem through theoretical physics. Human consciousness, while limited in its observational reach, possesses the remarkable ability to transcend those limitations through abstract reasoning. This ability suggests that consciousness plays a unique role in the universe, not as the primary audience for cosmic processes, but as the phenomenon through which the universe becomes aware of itself. Through human minds, the cosmos develops the capacity to understand its own structure, even in regions where direct observation fails. We become the universe's way of knowing about the parts of itself that exist beyond any possible direct experience. The invisible boundary of the Oort cloud also represents a kind of cosmic test of human maturity. Can we accept the existence of vast realms that will never yield to direct exploration? Can we build our understanding of the cosmos on foundations that include permanent unknowables? Can we find meaning and purpose in a universe where the majority of reality exists beyond human reach? These questions touch on the deepest issues of human existence: our relationship with the unknown, our capacity for faith in the face of uncertainty, and our ability to find significance in a cosmos that extends infinitely beyond our direct experience. The Oort cloud becomes a mirror in which we see reflected not just the structure of the outer solar system, but the limitations and possibilities of human consciousness itself. Perhaps the most profound implication of the Oort cloud's invisibility is that it reveals reality to be far stranger and more wonderful than direct observation alone could ever suggest. The universe is not just the collection of things we can see and measure. It is a vast, interconnected system of relationships, processes, and structures that extend far beyond the boundaries of human perception. In recognizing the existence of invisible cosmic realms, we acknowledge that reality is not constrained by the limits of human observation. This recognition opens up new possibilities for wonder, humility, and wisdom. We learn to appreciate mystery as a permanent feature of existence, rather than a temporary problem to be solved. The darkness beyond the Oort cloud is not empty. It is full of secrets, processes, and realities that exist for their own sake, rather than for human understanding. In accepting this darkness as a fundamental aspect of the cosmos, we paradoxically expand our sense of cosmic belonging. We become participants in a universe far grander and more mysterious than our direct experience could ever reveal. And so we return to our original question: why can't we see past the Oort cloud? The answer, we now understand, is not simply about technology or distance. It's about the fundamental nature of reality itself. The Oort cloud exists at the intersection of the knowable and the unknowable. It marks the boundary where our sun's gravitational influence fades into galactic darkness, where light becomes too dim to illuminate the cosmic architecture around us, where the laws of physics themselves conspire to create an observational horizon beyond which direct knowledge cannot pass. But perhaps this boundary is not a limitation, it's a revelation. It shows us that the universe is far grander than what we can observe, that reality extends infinitely beyond human perception, that consciousness, for all its remarkable abilities, remains a local phenomenon in a cosmos that operates primarily in darkness. The trillion objects drifting in the Oort cloud follow their ancient orbits, whether we see them or not. They respond to gravitational forces, participate in cosmic recycling, and shape the evolution of our solar system, all without requiring human observation or understanding. This is not reality's edge. It's reality's reminder that existence does not depend on observation, that the cosmos is not primarily about us, but about processes and structures that unfold in realms beyond any possible human experience. Hiorn. The Oort Cloud teaches us that the most profound cosmic truths may forever remain invisible, hidden not by technology's limitations, but by the mathematics of light and distance themselves. In accepting this cosmic darkness, we find not limitation, but liberation. We discover that we are part of something infinitely larger and more mysterious than we could ever directly comprehend. The darkness beyond the Oort Cloud is not empty. It is full of wonders we will never see, processes we will never witness, harm realities that exist for their own magnificent reasons. It is looting this bid of sea. This invisible boundary doesn't mark the edge of reality. It marks the beginning of everything we can never know, but can still revere. What do you think lies in that cosmic darkness beyond our sight? Are there aspects of reality that should remain mysterious, or should we keep pushing the boundaries of the observable universe? If this journey into invisible realms has expanded your sense of cosmic wonder, I'd be grateful for your like. It helps others discover these mysteries too. And if you're ready for more adventures into the unknown cosmos, consider subscribing for future expeditions into the darkness between the stars. The universe holds countless invisible wonders waiting to challenge everything we think we know. If you're ready to venture further into cosmic mysteries that exist just beyond perception, explore our other videos where we map the hidden architecture of reality itself. Each story reveals another piece of the vast, invisible cosmos that surrounds us.